Okay, shalom, hello. I want to thank the organizers for inviting me. I'm still thinking about everything I've heard in the last few talks, totally different domains than my own. And it's going to take me a little bit together with you to shift, because this is quite a big shift from what I prepared. And what I'm going to try and do in the next few minutes that I have is to show you what we do when we actually develop, using AI or using deep learning these days, solutions to some specific tasks in the medical imaging area. And so if I see the different symbols that were used here, I'm the optimistic one. And I'm busy developing new capabilities using deep learning. And I definitely appreciate all the people that are going to try and help us make sure that it's only used for good. Okay, because we can think about things that may be used in a wrong way, in a way that we don't want to. But let's see how we use things and develop things, and maybe that also helps us understand how we're using AI and what AI is. At least for me, that's the case. So I had the Medical Image Processing Lab, which now I call Deep Learning and Medical Imaging Lab, here in Tel Aviv. Okay, and we're busy solving or building tools to help the medical domain. Okay, so like we've heard, with these networks, we need a lot of data, and that is true. But as I'll tell you soon and throughout my talk, in medical imaging, we don't necessarily have a lot of data. In fact, I would not say that we are living in a big data world. And all our innovation is actually how to deal with the fact that we have limited data. And so when we entered this domain of deep learning, the medical imaging society, the field, we were very skeptical that it actually can be used in medical imaging. And as you see, a few years back, we were asking the question, are we going to actually be able to use it? And our first answers to this question came in around 2015. And then, very quickly afterwards, so this is a little bit of a historical timeline, 2016, we were already busy enough in different research groups around the world that the first special issue in our major journal came out on specifically this topic, how we use deep learning for medical imaging. And I was the lead editor on that special issue. And then came the first book in this space in 2017. Again, myself and two colleagues co-edited this book. And since then, there are many more books coming out, and the field is actually exploding, and the pace is very, very, very fast. So I'd like to share some of that, some of this excitement with you. Now, specifically, what I've been doing in the last few years is focusing a lot on radiologists, a little bit on oncologists, which is the next level up. Radiologists are the first medical practice practitioner that's actually sitting down and looking at an image. And these images can come from the ER. Can we see this mouse? No. Let's see if this will work. Okay, great. Could come from the ER, from outpatient clinic, and so on. All these images get stored in what's called a PACS, Picture Archiving Communication System. It's basically a storage. And then one by one, they are read by the radiologists. And as we have advanced in resolutions of acquisitions, so MRI machines are better, CT machines are better, the radiologists now need to read thousands of scans per patient, where a few years back they would read 10 scans or hundreds of scans. It's the same radiologist sitting, reading in the same way as they've always been reading, with their two eyes, scanning and looking for anomalies, as were said here before, things that are wrong, and so on. So there's a limited time to review ever-increasing number of images, And this is leading to missed findings, long turnaround time. And although we want advanced healthcare, they don't have time to sit down and give us quantification, measurements of things, which are important, of course, when we want to fight different kinds of diseases. So the question is, can we use our tools and start bringing them into the clinic? And I should say the tools that I'm referring to are image processing, computer vision, machine learning, deep learning. Okay? So we're hoping that we can start supporting and including and bringing our capabilities into actual clinical use. And what are our challenges again? So our challenges, the first challenge is that we have a limited amount of data, as I've said. So let me convince you why this is the case. So I believe most people are familiar with the term ImageNet. This is a data set of millions of images. And basically, using ImageNet, we have now all the networks, very, very large, deep, many, many layers of computational units or neurons that are trained based on these millions and millions of images that have been labeled. This is okay for what we call the classical computer vision, when we want to identify animals and many, many other things in the world. And see the difference here when we're talking about a medical imaging task. So when we want to help in detection of some lesions, when we want to characterize some lesions and so on, this is what we're facing, and this is working with collaborators that are interested to support us, looking for data in the hospital setting. And you see some of the problems here. First of all, collecting the data is difficult. We have all these issues of extracting the data, which actually we need support in. And we also work very closely with experts, so that makes the whole process expensive and slow and very, very difficult. So this is why our task is quite different than a big data kind of task. And I want to show you some of our solutions, and I believe that I'll give you some intuitive answers that you'll be able to follow me. And let me show you this in somewhat of a historical perspective of how we started. So around 2013, the hype began of deep learning. That's when the Computer Vision Society said, wow, we have millions of images, wow, we can identify all of these different types of images. It was a big, big jump in performance in what we call classical computer vision. So that's when we started looking into these tools, but we don't have a lot of data, so what can we do? The first thing that my group explored was the following. It's called transfer learning. How can we transfer information from what was learned in one domain, which is this natural image domain, animals, clocks, and so on, to our domain, which is the medical imagery domain. And we started looking at X-rays and trying to identify if things are wrong in an X-ray. Now, people were a little bit surprised why we're looking at X-rays, why not CTs, MRIs, they're much more interesting. Radiologists like to look at MRIs, they don't like to look at X-rays. Well, that's exactly the reason why we looked at X-rays. There are more X-rays in the world than any other combined modality, all the modalities combined. So X-rays are there. They're the first thing that is extracted to identify if something is wrong. And because someone sitting quietly in the emergency room may be waiting for too long because there's not enough radiologists to read all the X-rays, we are in fact losing patients. And this was told to us all over the world. The same scenario in every hospital in the Western world. We lose patients because there aren't enough radiologists looking at X-rays. And a patient sitting quietly in the emergency room is waiting too long. And something bad may happen. So let's look at X-rays. So the question here is if we can take a network and when we input an X-ray to it, will it know something about this image? Now, of course, I don't want to identify this X-ray as one of these categories. So what I can do is I can read out some representation from this network. And this is the vector that you see here. So I read out something from the network, and then I use a different kind of classifier to tell me if there is some pathology, yes or no. If there's this pathology, yes or no, and so on. You may even use a rule-based kind of system. And I'm able to come up with different labels for this case, and there are in fact quite a few pathologies, 3 different things here that are pathological in this case. So, would this give me any kind of interesting information? That was the question. Now, 3 years before this investigation, we were developing state-of-the-art technology. It's called Bag of Words. We were competing and winning first places using this technology. So we were quite skeptical. But a few weeks into our exploration, we saw this is our winning results, and this is what we can get within the network representation. As you see, it's as good or better, and this is just reading one layer from the network. So this was our first exploration, and this won an interest of the entire community, and this is where we started pushing forward and exploring more and more. Can we do something with these networks in the case where we don't have a lot of data? Okay, so I'll show you some more about limited data, but what happens now, slowly, very slowly, is that sometimes we get public data sets available. So you see here, 2017, NIH decided that there's enough interest in X-ray. Let's bring out a lot of data, hundreds of thousands of X-rays. So that's great. We're starting to have more data that we can work with. But what happens is that we don't have the experts sitting down and reading each one of these. Now we're relying on NLP, natural language processing, to read from the reports. That means that we're going to have a lot of noise in the labels. So yes, we have a lot of data, but the labels are very, very noisy. People have shown huge mistakes that are introduced to our ground truthing. What you see here is that our network competed quite nicely with what the authors of this, when they introduced the data set, were showing, so we were quite pleased. But really what we can do now, when we have a lot of data, is do what's called fine-tuning. And that means we can take a network. It has been already learning things from those millions of ImageNet classical images, but now we can show it a little bit of medical data, like a little bit of X-rays. So we show it in X-ray data, we give out the identification if there's any pathology in that X-ray data, and the networks, the way they learn, they sort of propagate back in error, and the weights of the networks adjust to each one of these examples that we show. It's called fine-tuning. Most of the learning was done with ImageNet, and with the transfer, but a little bit of this data that we now have we can use for additional training. And what you're seeing here is that we can now, a few years have passed, we are now dealing with 14 different pathologies, and we can even localize. So these are outputs of the network showing us where they found the pathology, and we're at a 90% sensitivity and specificity. And if we are able to get systems out there that between 80 to 90% sensitivity and specificity, this is becoming clinically relevant. If we have such systems, we can start putting them and supporting the clinicians. What is happening these days is that there's more and more excitement about the idea of transfer learning. And people are saying the following: if systems can learn from any kind of image, and now it's just seeing another image, and then it's fine-tuning a little bit on that image, and it's getting better. What happens if we train it not on the natural images? Let's train it now on a huge amount of X-ray images. In fact, we have all these 14 categories in the X-ray database that we received. And what you're seeing here is the following experiment. This is the image, a network that's pre-trained on ImageNet. And the question is if the image has tuberculosis or not. Now, tuberculosis is a very important finding, but it happens not to be one of the 14 findings that we have data for in the NIH data set. So the second option is now to go and continue training the network from this classical images to these X-ray images, learning 14 categories, and asking the following question: if a network has a lot of domain-related examples, okay, so it's X-rays, it's different kind of X-rays, it doesn't have tuberculosis, it has lots of other things, will that help us identify the disease that we're interested in? And these are kind of things that may be called domain transfer, and you can think that it really relates to the way we can envision our own brain learning from situations to situation, becoming better and better as we progress in time and see more and more images. So we're trying this on 2 data sets. One we use more for training. This will be totally untouched and only used for testing. Here you see some cases of tuberculosis. And what we see is that we got an increase of certain percentage when we use a pre-trained network that was also trained on the X-rays. And moreover, when we use another data set that we've never seen before, it's coming now from a different, it's coming from a different hospital. So that sometimes makes things decrease substantially. So suddenly we're seeing images coming from different scanners, different hospitals, and so on. In the case where we've seen enough X-rays, it's quite more robust. And that's where this field is heading, which is better and better training. As many data sets as you have, continue training the networks. And yes, we understand what we're getting in the lower levels of the networks, what we're getting in the mid-levels of the networks, and so on. And we can continue and improve those network connections with more and more data that is tuned to the task. Let me now shift to another domain that my lab is focusing on quite a lot with collaborators from Sheba. Michal Amitai is the head of CT abdomen unit at Sheba, and we work a lot with them on liver CT. So what you're seeing now here is a CT, and you're seeing the liver as through the slices. This is us segmenting out the liver. And the question is the following: can we help them detect lesions in the liver? Can we then classify the lesions in the liver? And you see here different categories. And can we even give them some helpful advice for treatment, which usually means understanding if the lesion is malignant or not. So here's some, we have a lot of works on this. I'm just showing you some results on how we're now able to detect lesions of different sizes, different characteristics quite accurately. So this has been done very well. And I want to focus on how we classify lesions, okay? So here's a task. We're given these data sets of lesions, and you see the amount, very minimal, very small amount. Cysts are benign and easy to identify. Metastases are malignancies we really need to identify. Hemangiomas look very similar to metastases, but in fact are benign. In one case, you have to tell the patient, you have cancer somewhere in your body. We see the metastases in the liver. You're going to have to now to go and try to check where the cancer, the primary cancer is, and then go on for treatment and so on and so forth. And the other, we just send home. Totally different treatments. Totally different outcomes. So the distinction here is very critical, and radiologists would very much like some support in making those decisions. But if we try to build a network that takes one of those images and has to identify one of these 3 categories, we're limited by only this amount of data. That's nothing we can work with, okay? This doesn't help us learn a network, which means identifying all these connections and weights, and there are millions of parameters here that need to be learned. This is what we mean by learning the network, teaching the network. So how can we get more out of what we do have? It's called data augmentation. So that's the second trick I wanted to share with you. One was how we transfer information. The other one is how we augment information that we have. Now there's the classical augmentation, and that is something everybody does. So if you give data, we'll get more data out of it, on the order of 100-fold. It doesn't really matter which kind of data. I'm sure in all different situations, all different data sets, you generate a little bit more data from what you have. In images, it means you just rotate slightly, and you can flip, and you can do a lot of different small things to the images. But this is the new area of synthetic augmentation, and maybe you've heard about it today. I'm not sure, in the morning possibly. Generative adversarial networks. In fact, I know you did, because I saw the adversarial thing going in the wrong direction before. Okay, so let's look at it in the positive direction. So we want to use GANs, for short, to generate artificial data. And in classical computer vision, people generate artificial looking cats, dogs, change one face to another face, style transfer it's called, do a lot of different things, color to gray, all sorts of things. What we want to do in the medical space is generate lesions. And in fact, we were one of the first groups that did that. So here you see a little bit more about the complexity of building such a network. It's quite involved in a lot of variations of this architecture. And here you see results. So these are real lesions, and these are synthetic lesions. Okay, and here are some more synthetic lesions. Now, I don't have time to talk about the entire work we've done. We did show this to radiologists. We have a lot of interesting experiments for giving the radiologist true lesions, fake lesions. The bottom line is they cannot identify which is which. And several other kind of experiments have shown us that we do not include here any major artifacts or things that should not be present. But really, as engineers, not coming from engineering, our goal is to use this to make a system more robust. So my interest is to see if I add more data with this synthetic data, can I get better results in a system? And this system that needs to identify between these three categories, you see some results here, and this is like the weighted average. This is the earlier technique that we had. This is the network with classical augmentation, and this is with the new systems with more data. And in fact, we were able to show huge increase in performance. 7% increase is amazing. It's a big delta forward. So yes, we're able to generate data from the given data to help the systems learn more. In fact, nowadays, amazing things are happening. People are trying to convert CTs to look like MRIs, MRIs to look like CTs. More importantly, they're taking very low-dose CTs and making them look like they're high-dose CTs, which is really exciting and critical, and so on. A huge amount of interesting things to do. What we explored further is what we call, what's called like a PET-CT connection. So PET, as you see here, it really shows quite strongly where the malignancy is in the body. And there are PET machines that are PET-CT, they're combined with the CT image, but not always available, and these are the issues with the PET. It's radioactive, it's expensive, and so on. So we don't always have a PET. If we did, the identification of malignant versus non-malignant would have been much easier for the radiologist. So what we've done is we looked at the pairs of CT and PET that we do have. These are pairs that we have, PET-CTs. And we basically built a network that generates artificially, given a CT image, a PET-like image. Now, this has not gone through radiologists, and it's a very early stage of development. I would not treat it as a real PET image, but rather as kind of a mask that tries to imitate what the PET image would identify as strong active region versus regions that are definitely not active. And the way we can use it in a system is by including this mask here to remove lesions, candidates of lesions that we know for sure are not malignant. Okay, so we use this mask to erase things that may be false positives, and in fact, we increase performance by almost 30%. So this is where we're heading, a huge amount of opportunities now in making systems at the level that they can enter the clinic. They're much more robust, we can reduce false positives, and a lot of this is with the help of these deep networks, which we do understand how to improve further and further and further. I'll say one word about a different challenge, which is the fact that the annotations are noisy. So I mentioned that annotations could be very noisy, and this is work that's just starting, so I'm skipping a lot of it. But for those of you that may be able to follow here, the idea is that we're adding basically a layer to a given network, and this layer is going to symbolize the noise. It has a few more parameters that need to be learned, and once we learn this network now with an additional layer, we are able to then, in the test case, find the true output Y, although we train on noisy label Z. Okay, so this is for people that may be able to follow me right now. I know it's very quick. And here's an example of how we use it. Benign malignant in the case of microcalcifications in the breast. So these are from mammogram data. Very difficult to identify if it's benign or malignant. One of the more difficult cases. And here we see a 5% increase by this technique of starting to model noise that we may have in labels and so on. Okay, so I need to use this mouse. Otherwise, we won't be able to skip. Okay. Come on. Here we go. Okay, so the last minute, I want to say that because we're at this level of, I could say success, there's a lot of companies that are now involved in making all these different algorithms shift to the industry. And there's many of them, also many in Israel. Different things they can do with the different algorithms, like alert if there's a finding for that person sitting there with the x-ray, or help the radiologist read faster so that he can do more important things than just find little lesions and so on. And studies are coming out like this one that are starting to look at the impact of the different tools that we can now provide on efficiency. And for the first time, we're seeing that this, in fact, has a lot of potential value to the real clinician. And that is why there's a lot of optimism that we are, in fact, going to be able to go very quickly in the clinic. These are some of our challenges that are remaining. Huge challenge is the data. But really, for people here and in this conference, we need a lot of help with enabling us to get more data from more hospitals, being able to open up data sets, both in terms of security of the patients, in terms of profit, who do we pay, who needs to get paid, and all of that are very interesting issues that we're not treating at all, but we definitely need the help in those. And then we can go ahead and do very important things like tracking information and really predicting diagnosis, treatment support, and so on. So thank you very much for your attention.